Hey there, YouTubers!
Dude, you should totally jump.
Excuse me?
Yeah, I just got done jumping and I'm totally fine.
Well, worst case scenario, I end up with the double.
Whoa, wait. Alright, what does a loose representation of peer pressure have to do with pressure? Well, only other than the word pressure about it. In the meantime, I'm just got to a rehab center. Holy crap.
Hi there! Dr. Sheep here. So what did that last skit with the kid jumping off a bridge and the jokes were kind of on edge? What did that have to do with today's topic? Well, it was peer pressure. Other than the word pressure, basically nothing. So today we're talking about pressure. Now, we've talked about pressure on my channel before. With the air cannon, anytime we're talking about PSI, that's pounds per square inch. And crushing soda cans with science, which is an old video that you can definitely go check out, but we're going to do that experiment in this video again today. So if you don't want to go watch it, I understand. Anyways, but I'm not really going to explain it too much as to what happened in the, well, I guess I'll have to. Anyways, so pressure can be broken down into force divided by area. What is force? Well, we've talked about force before. That's Newton's second law of motion. Force equals mass times acceleration. And that's pretty straightforward. We've talked about it before. Newton's second law. Definitely go check it out. We talk about rockets. So very, very entertaining video and educational. Anyways, so the unit for pressure is pascals. And pascals is newtons divided by meters squared, which is force divided by area. So if you have a very large force in a very large area, your pressure is very small. If you have a very large force in a very small area, you end up with a very high pressure. That's how knives work and bullets. Bullets are a very small area, but they're traveling very fast. Well, they're technically decelerating, but they're traveling very fast and have a large amount of force behind them. And so when they hit you, that implies a large pressure and causes a lot of damage. So we're going to talk about knives, we're going to talk about soda cans, we're going to talk about all kinds of stuff when it comes to pressure, so stick around. Welcome to the Dr. Sheep cooking show. I have a cutie here, and we're going to cut it with a knife. Now, we have the blunt edge here, because as you can see, it's not cutting my finger. And then we have the sharp edge here. I will not hit that with my finger. Anyways, so the blunt edge, as you can see, will not cut the cutie. No matter what I do, it won't. But as soon as I take the sharp edge here, about chop my fingers off. Now, ladies and gentlemen, be careful when you're doing this. But watch. See, I can force quite a bit and it won't. But as soon as I, well, there we go. And it cuts. See? And now I can peel my orange and eat it too. So, provided it's sharper, it will cut it much easier than what I showed. But, see, the sharper you get that edge down there, compared to this blunt edge, the easier it is to cut things. Like I said, area, force over area. Well, I did lose a finger. Kidding. Of course. I did lose a finger from cutting that orange. Nearly did. But after doing that, I acquired some insightful math. Oh, measurements, I should say. So, I didn't really care about the mass and acceleration. I just picked a random number, 22 newtons, which is about 5 pounds of force. Anyways, so on the doll side, we each one have 22 newtons of force. I measured the length of the cutting area is about 0.015 meters, and the width of the blade, or the width of the dullness of the knife, is 0.002 meters, which, when we multiply all of that out, we're looking at 165 pascals, which is like nothing. Absolutely nothing. And the sharp side, again, sticking with the same length of cutting area on the orange and the same force, but we have a drastically smaller width of the blade at 0.5 millimeter or 0.0005, sorry, 3015 meter, and that is 660 pascals, which is far greater than this 165. Because remember, we're looking at 2 millimeters thick here. We're looking at 0.5 millimeter. So we're looking at a fourth of the size. So yeah, this is just knives here. Let's move on to air pressure with an old experiment you've all seen me do on my channel before, if you're OG. Why, hello there. I'm in my fun fact chair. I have my fun fact book, which means it's time for a fun fact, or facts. So, according to the website I found, it's a physics textbook, apparently, the blow your nose is 8.8 kilopascals. That's 8,800 pascals. And the urge to urinate is 3 kilopascals, or 3,000 pascals. That seems like a lot, especially when we compared it to our knife earlier. But isn't that just fascinating? Welcome back to Cooking with Dr. Sheep. Now we're warming up water on a stove and some LaCroix cans. Now I'm going to demonstrate the crushing power of the atmosphere. So what I'm looking for is the steam start rising out of one of the cans. Safety first. So I have some thick gloves, I have a bowl of cold water, and I have this big thick glove. What is steaming? This one looks like jelly a little bit. Got it now. Ta-da! It was melting my gloves a little bit. Well, let's do that again just for the fun of it. And it sucks up the water in there as well, because the air pushes down on the water in the bowl and pushes it up into the can. Oh, it didn't crush the can, but it filled it up with water. Not as cool, but still works. Wow, what an OG experiment. I find that one just somewhere on my top favorites. Anyways, so let's break this down into the math, shall we? So our can has a diameter of 0.066 meters. And so the area of a circle is pi times the radius squared. So we half the diameter, which is 0.033. We square that, multiply it by pi, you get 0.034 meters squared. Now, for every square meter of air, there are 10,000 kilograms pushing on it. So, if we do a little bit of cross multiplication, we end up with, drumroll please, we end up with 340 kilograms pushing on the top of that can. And with nothing put on the inside pushing outwards, this crushes the can. But why is there nothing? Well, I put a small amount of water in the bottom of the can, and I explained this in the video I do this in, but I'll explain it now. I put a small amount of water in the bottom of the can. I heat it up, that turns into steam, which fills the can. I turn the can upside down to a bowl of reasonably cold water. This rapidly cools the steam. The steam condenses back in the water, and water takes up far less room than steam. This creates a minor vacuum inside the can. Therefore, the pressure is, there's a massive pressure differential between the air and the can. The can gets crushed, and also the weight of the air pushes the water up into the can and fills the can where the steam once was. Wow, that's a lot. But now it's time for my favorite part of any episode. Now it's time to supersize. We've explored a knife cutting through an orange. We've talked about air pressure. Now it's time to supersize. I have my truck here. This baby can hold 5 people. And we have a LaCroix can to compare it to the air pressure. We have a rock, and then I have some peanuts, because if I can't get them, if this thing can't open those peanut shells, nothing can. It's also kind of kicks and giggles. All right, let me get inside real quick. Now that's a lot of damage. Hey, look, it opened it. Still good. Maybe not these. This one's still pretty good. Oh. But as you can see, a rock is unaffected. Wow, wasn't that exciting? We crushed a soda can, tried to crush a rock, and we opened some peanuts for me to eat. Man, those are good peanuts. Anyways, let's crunch the numbers, shall we? Alright, so I estimated that my vehicle weighed about 1,400 pounds, which is 20,017 newtons. Divide that by 4 to get the newtons per tire. We get 5,004.25 newtons per tire. Then, let's try to find the area of which the tire takes up, which is about 2.4 meters by 2.4 meters, and that's a rough estimate. I mean, the number we get in the end really, for how big it is, really doesn't matter. Anyways, we multiply those two together to get 0.0576 meters squared. Now, we take this divided by this to get, drum roll please, to get 86,879.34 pascals. Woo! I really actually don't have anything to estimate that by. That's probably going to be brought up in the fun facts segment. So you've already seen that, what this compares to. But that's a lot of pressure. Well, let's wrap things up. So we start today off with simply cutting an orange and how knives work, to eventually crushing soda cans with science and how much air pressure can actually affect things here on Earth, and thanks to our bodies we're open systems so we don't get crushed by the atmosphere. And then we supersized it up to how much force I applied, well, how much pressure I applied to that soda can, that rock, and those peanuts. Pressure affects us every day, from breathing to opening a soda can, because a soda can contains a higher pressure on the inside than the outside. Pressure is more essential than you realize. Pressure differentials allow you to breathe. When you breathe in, you increase the volume in your chest. This creates, again, a void which air wants to rush in. That way you don't get crushed. And then you breathe out, which increases the pressure. So to equalize the pressure, you release air. Pressure affects us every day. As I've already said, it's fundamental. But in the meantime, I would like to thank you all for watching. Please like, comment, and share. New videos every other Friday, and good night. Step 3. Maybe I should consult my book. Oh, hi there! Didn't see you there. Bet you didn't see me, because I know nobody's watching. Ha 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 ha. Because I have everyone want right now, like how to make money from YouTube. Yeah, you should totally subscribe, please, and check the playlist wherever it's gonna pop up. Jeez, this is getting awkward. Bye.